What we're going to do in this section is start um, changing the language from systems of linear equations into systems of matrices. And instead of eliminating by subtracting one equation from the other, what we're going to do is multiply with a matrix. So we are translating from algebra, basic algebra, where we multiply and subtract, to algebra of matrices. That's what we're doing. Um, so again, our goal is to get to algebra of matrices as opposed to algebra of equations. So again, um, we're going to go from algebra of equations into algebra of matrices. That's our intended goal in this section. The thing is that if we understand matrices very well, then this turns out to be fairly simple. Let's start with a very important matrix. I'm going to label this as example 0. Example 0. And that is the identity matrix. Identity matrix. There are actually more than one identity matrix. I didn't use plural because it's understood that there is one for each dimension. So all identity matrices are square. All identity matrices are square. All right. So the 2 by 2 identity matrix has ones in the main diagonal and 0 everywhere else. And what it does is that if you multiply with any matrix of any size, A, B, C, D, E, F, well, as long as it is a 2 by something, 2 by 1 or 2 by 2 or 2 by 3, we end up with the same matrix. So A plus 0 is A, B plus 0 is B, C plus 0 is C, and then no A and a D, no B and an E, no C and an F. By the way, if we were to shorten this matrix by one column, so one fewer column, the same thing will happen here. That is an interesting observation. So when we multiply a matrix with a matrix like this one, it doesn't matter how long it is, we will still have the same patterns on the first few columns. So again, if we shorten this, then that will be shortened in the same amount. In fact, if we omit this guy, then this will be omitted. Yeah, we will talk about this when we talk about augmented matrices in this video. If we want to multiply by a matrix that has 3 rows, then the corresponding identity matrix will be one that is 3 by 3. So we want to have ones on the main diagonal and zeros everywhere else. So if we multiply by, say, A, B, C, D, E, F, there we go. So let's understand what this is doing. Because of the zeros, we're picking up just the first element, A, and then nothing else. And then as we go down, we are picking up the second element here. So we're picking up the first element, the second element, and the third element of each one of those columns. So again, the first element, second element, because there are zeros, and then the third element of this column. And the same thing will happen here. We're picking up the first element, second element, third element. So this is exactly the identity matrix that is a 3 by 3. Now, if we have an extra column, we would be doing the same thing. We're going to be picking up the first element of that extra column, the second element, because the other two parts of each one of those rows is 0, we're only picking up the second element and the third element of that next column if we had one. Yeah, so that's another way to think of this, picking up the first, second, and third in that order. Yeah. So we will have A, B, C, D, E, F. Now let's switch two of those rows. So if we put down 0, 1, 0, 1, 0, 0, and then leave the last one alone, 0, 0, 1. So we are switching two rows. This is not an identity matrix. So mind, this is not an identity matrix. Not at all. But let's see what it does. Yeah, because we want to understand what the matrices do to other matrices. At least up to a point we want to understand. So what this matrix does is, okay, as we start multiplying through, it picks the second element and places it first. And then let's stay with this column. And then we pick the first element. And then we pick the last element because the other parts of these rows, of those rows, are zeros. So E. And then when we move on to the next column, we're picking up the second element again, D. And then we have B plus 0 plus 0. And then F. So notice what we have just done. AB is placed together, but on the second row. And CD, so this move down here, is placed on the first row. So this matrix acts on this matrix by swapping the first row and the second row. And the third row remains intact the way it is. Isn't that neat? So we're learning how matrices affect other matrices. Yeah, they act on them. All right, so now let's move on to an example. Example 1. All right, so let's say we have the system of equations x plus y equals 7 and 2x plus 3y equals 8. We want to write this as a matrix system. So we have 1, 1, 2, 3. The coefficients are 1, 1, 2, and 3. X, y equals 7, 8. Now remember, typically what we do is, let me remind you what we typically do. We multiply this by 2, so that is going to give us 2x, 2x plus 2y equals 14. And then we have this guy, 2x plus 3y equals 8. And then we subtract the 2. So 2x minus 2x is no x. 3y minus 2y is a single y. 8 minus 14 is negative 6. All right, but we want to do that without, again, let's go back to the goal. We want to change or go from algebra of equations, that's algebra of equations, into algebra of matrices by multiplication. So we want to find a matrix that does this on the matrices. Instead of doing that, we want to be able to subtract twice the first row from the second row. Yeah. So I'm going to tell you what matrix to use. So start out with a main diagonal of ones, just like the identity. But we're going to take away 2 of the first row from the second row. Now let's see if that is working. Let's actually multiply those three and see if that works. Okay, so we take 1. So this 1 picks up just the first, and 0 picks up the first component. So it keeps this row intact. We're going back to this kind of thing. What do matrices do to other matrices? For instance, this one exchange those two rows. So, but if you keep it just as 1, 0, 0, that keeps the row where it is. So this matrix just keeps this row intact, intact, intact. We're learning how the rows of this new matrix, which is, well, this is the identity matrix, but some other matrix affect the matrix we multiply with. All right, so this 1, 0 keeps those two alone, doesn't mess with them. Now, let's understand what this does. This one takes the first row, multiplies it by -2, and then adds it to the second row. So it takes the first row, because of the -2, multiplies it by -2, which is the same thing as subtracting here twice the first row. So it takes the first row, subtracts, the negative means subtracts twice as much of this, and adds it into the second row. Well, let's see. -2 times 1 is -2, plus 2, 0. -2 times 1 is -2, plus 3, 1. There we go. So it leaves the y alone. But we're not doing this with algebra of equations. We're doing this with algebra of matrices. So this represents x plus y when we multiply with xy, and 0, 1. Now, when we do this to the left side of the equation, we have to do exactly the same thing to the right side of the equation. So we multiply 1, 0, -2, 1. So I just told you which one to use. If we want to subtract twice as much of the first row from the second row, put -2 here. Yep, and leave the 1 there. So we have 1, 1, 2, 2. Oh, but now we want to see what happens with 7, 8. Yep, 7, 8. So we have 7 plus 0, 8. So that's 7. And then -14 plus 8 is -6. All right. So this is what's going on. Take this system of, or this equation of matrices. We're going to multiply on the left by 1, 0, -2, 1. 1, 0, -2, 1. 1, 1, 2, 3, x, y. And that's going to be, again, 1, 0, -2, 1. We have to multiply on both sides of this equation by the same matrix, which is this one. 1, 0, -2, 1, 7, 8. Now, the multiplication of those two we just did up here. It is going to give us 1, 1, 0, 1, x, y. And then the multiplication of that matrix with this column vector we did up here. That's going to give us 7, -6. All right, so we multiply both sides of this equation, of this equation rather, by 1, 0, -2, 1. There it is, 1, 0, -2, 1. When we multiply, we get this matrix. When we multiply, we get this matrix. And now it is easier to figure out what the variables should be. Well, y, because when we multiply, we just end up with x plus y and y. And then we can do back substitution. So y is going to be -6, as we already learned up here. Y equals -6. And if x plus y is 7, but y is -6, so we have to start out with a bigger number so that when we subtract 6, we get 7. Well, that number has to be 13. So x equals 13. Let's just make sure. 13 minus 6 is 7. 26 minus 18 is 8. Yeah, so that works. Now you may be thinking, whoa, that's much more work. You know, this was easy. This was easy. We already got the -6 in really a quick period of time. This seems way more complicated? Yes, it is, because this equation is simple. Had the equation been more complicated, maybe that wasn't as complicated, one. And two, we're not doing this just to solve equations. We're learning this so we understand matrices better. We want to build an intuition about matrices, how they interact with one another, how they change things, because matrices are used extensively in many other places. So we're not doing this. The motivation is not just to solve equations. The motivation is to understand matrices in more depth also. Oh, there's one other thing. Notice that here we had to do this computation and this computation. And really, we were doing the same thing, the first component, just write it down, because then we add 0 to it, the first component, and we did the same thing, the first component, and then add 0. And then we took -2 times this component and added to the second component, and same thing here. And so did we did the same thing here. So oftentimes, instead of doing two computations like that, we use what is called the augmented matrix. Sometimes some people label it as, A, which is this initial matrix. Let's label this as A. And a lot of people, a lot of books label this as B. Yep. And so this is the X. And those are two vectors, of course, and that's a matrix. So, and the augmented matrix, they just put A and B. Sometimes they put a column in between, but it doesn't matter. And this is what it does. Let me build a little bit of space down here. So instead of having the square matrix and the constant matrix, since we're going to do the same operation to both of them, might just as well do them once instead of twice. Actually, I'm going to rewrite. I'm going to continue on the next page. Yeah. So we build the augmented matrix corresponding to the system, either one of the two. So the augmented matrix will be 1, 1, 7. Mind 7 is, sometimes people put a dotted line, corresponds to this guy, to the constant matrix. And then we have 2, 3, and then 8. So this is the augmented matrix corresponding to this system of equations, or to this matrix equation. And so instead of multiplying this matrix twice, for this guy and for that, let's just do it once. 1, 0, -2, 1. And that's going to give us, let's just do it again, even though I already have the answer here. Let's do it again. So 1 and 0. -2 plus 2, which is the goal. We wanted to eliminate this element. 1 and 0. And then -2 plus 3. And then 7 and 0. That is the corresponding one to the column corresponding to the constants. And then -14 plus 8, -6. So instead of doing this multiplication twice, we can do the multiplication once, keeping in mind that these are the coefficients of the system, while that is the column of the constants. Yeah, sometimes we save time because then we don't have to do this twice. Um, it is when we do something too systematically, um, then what I mean by that, if we use a formula, a shortcut too often, that's what I meant to say, then sometimes we forget the meaning behind what we are doing, or how things are working together. So at the same time, we don't want to dwell too long on computation. So we want to find the balance between um, doing everything from scratch, and doing everything just by formulas, because just the formulas makes us miss the understanding of what's going on. And doing everything from scratch, well, is not very effective or practical. So we have to have some balance between the two. Um, let's look at a second example. Um, this time I'm just going to write down the matrix 2, 1, 7, 4, x, y. The matrix equation equals 5, 6. Okay. So remember, this really means 2x's plus a y equals 5, 7x's plus 4y's equals 6. And we want to figure out the x and the y. However, we want to do this via algebra of matrices. We want to get away more and more from eliminating using equations, but rather using matrices, multiplying matrices to achieve the same thing we achieve with the same thing we obtain when we use elimination of equations. So what we want to do is eliminate this guy. Yeah. So then we will have a straight shot to figuring out y. Okay, so what we need to do is multiply both sides. I'm going to do this at once. I'm going to multiply 1, 0. Okay, so we need to multiply this guy so that when we subtract from 7, we end up with 0. But this is already 2. And I need to impose a 7 to match the 7. So we need a 7. But we need to get rid of the 2. And we need to subtract. So this is the way I do it. Again, we need a 7. So we impose a 7 on this row. We need to get rid of the 2 because we don't have 14. This guy is not 14. This is 7. So we need to get rid of the 2. And unfortunately, we have to divide by 2, which causes us to have a fraction. It's a little added complication, but we can handle fractions. And then we need to subtract. So that's why we put a 0. And that's it. That will cause this 7 to go away. 2, 1, 7, 4, x, y. So I'm copying this equation, but we are multiplying on both sides of the equation on the left by that matrix. So we have 1, 0, negative 7 over 2, 1, 5, 6. Okay, so let's go ahead with this. This is going to add a little bit of a complication when we multiply with a 4, but that's okay. So let's multiply those two. So 2, nothing. We're going to end up with 2. 1, nothing. So that's 1. 2 times negative 7 halves is negative 7. Plus 7, 0, which is what we intended. Again, 2 times negative 7 halves is negative 7s because the 2's simplify. So we end up with negative 7. And then as we move on to the next multiplication, we end up with 7. Negative 7 plus 7 is 0. Well, here we're going to have negative 7 halves plus 4. Negative 7 halves plus 4. I'm going to do that computation on a different piece of paper. I guess I'm going to start putting together a little bit of side work, side computations. Again, negative 7 over 2 plus 4. Many of you who are listening to this video probably already figured this out. Um, Plus, of course, that is 8 halves, and that is equal to 1/2. But just to be sure, we want to show how we computed the 1/2. So that goes here, 1/2 xy. And then we're going to do the same kind of operation here. 5, nothing. Negative 7 over 2 times 5 plus 6. Negative 7 over 2 times 5 plus 6. That is exactly what we are multiplying here. Negative 7 over 2 times 5 plus 1 times 6. Well, that is negative 35 over 2 plus 6. But the 6 can be written as positive 12 halves. And that is negative 23 over 2. Negative 23 over 2. All right. So we succeeded at having an upper triangular matrix that gives us a direct shot to figuring out y, because half of y is negative half of 23. Well, that means that y has to be negative 23. Again, that is a direct shot. And 2x's plus a y equals 5. Well, y is negative 23, so this guy has to be reasonably large to get 5. So because whatever the 2x rather, whatever the 2x is, minus 23 has to be 5. Well, so that means we have to have 28 for the 2x, because whatever that number is has to be more than 23, so that when we subtract 23, we still end up with positive 5. So we have to have 28. And that means that, but that is twice x, so that means x has to be 14. X equals 14. So there is our solution. Another way to write this down is by stating that xy is 14, negative 23. Now we should check that on the original equation. So 2 times 14 is 28 minus 23. Sure enough, that is 5. 7 times 14, that's 98. 98. And then 4 times negative 23. Boy, this is getting, so let me write this down. 7 times 14 plus 4 times negative 23 is equal to 98 minus 92. So sure enough, that is 6. So it works out. But again, we are getting away from using these guys, using equations, and instead we're using algebra of matrices. No more algebra of equations. And I'm not saying they're prohibited. We're getting away from them, and we are looking into algebra of matrices instead. Let's do a third example. Yeah, a third example. Let's say we have 432, 431, 325 multiplied with x, y, z to obtain, I don't know, 9, 10, well, 10, 11. I just made that up out of the blue. So hopefully it will work out nicely. Whoa, this is going to get longer. Um, at least we can get started though. Actually, it shouldn't be too bad because all we need is three matrices. We need to get rid of this guy. We need to get rid of this guy to end up with zeros. And then we need to get rid of this guy. Interesting. So this, and that. Well, based on what we did in the previous examples, what we need to do is get rid of the 4. So we need to subtract those two. Yeah, and it's a straight subtraction. We don't have to multiply by -7/2 as in the previous example. That was kind of a fraction. Now, I'm not saying there's no going to be any fractions here, but at least in the first step, we don't have any fractions. So we're going to multiply on left, that is very important, of both sides by 100. That means we don't want to get rid of this guy, and we want to take away the first row from the second row. So we have the identity matrix, one's in the main diagonal, but this indicates that we're going to take the first row and take it away from the second row. Okay, let's see if that is true. Now I'm going to multiply the augmented matrix. Instead of multiplying on this side and on this side, as we did in the previous example, remember? So we multiplied on both sides of the equation, and that multiplication was not too hard, and we got to this, and then this multiplication got to that. I'm going to consolidate the columns. We have 1, 2 columns, and a third column, and I'm going to put them together in what is called augmented matrix, instead of multiplying on both of them, on both sides of it. So the augmented matrix will be 4, 3, 2, 9, 4, 3, 1, 10, 3, 2, 5, 11. And we're going to multiply on the left by 100, -1, 10, 001. This is a 3 by 3 multiplied with a 3 by 4. We're going to end up with 3 by 4. Hopefully I have enough room here. Anticipating I may not. So let's scratch this. Let's multiply, and I put the product here and see what we get. So this is the augmented matrix because it has an extra column which contains this one. All right, so this picks up this row picks the first element straight out. So 4, 3, 2, 9. So we're going to end up with 4, 3, 2, 9. Second row picks this first element, multiplies it by -1, and adds it to this second element in this column. So -4 plus 4, 0. And then there's another 0, so that does not affect the rest. -3 plus 3, 0. -2 plus 1, -1. -9 plus 10, +1. And then we're finished with this row, multiplying this row with all of the columns. Now let's multiply this row with all of the columns. Well, there's a bunch of zeros and then a 1, which means we're just picking up the last, of these columns, the last entry. So 3, 2, 5, 11. Excuse me. By the way, books have some kind of notation for this. I want to make this a little neutral. So I'm not going to write down a notation, like some kind of subindex that tells you you know, that we're subtracting the first row, the two rows, the first two rows are involved in this operation. So I'm not gonna, uh, it is your job to figure out the corresponding notation to different books we may be using. All right, so yes, this is more triangular. Now remember, this is just riding along, and it's not necessarily a bad thing because we were going to multiply by that column, but technically that is a different multiplication because that is on the other side of the original equation. We were going to multiply this matrix on the left here and on the left there. But since the matrix multiplication behaves the same way with the columns, might just as well tag that along. And that way we don't have to do that multiplication on this side. But remember, that is just the other side of the equation. Okay, so now we got this new matrix. Now, can we get rid of this guy? And the answer is yes. Okay, so here's where we may have to use fractions. I want to make sure I have enough space, so I'm going to use a new sheet. Okay, so this is, by the way, the first matrix we had. And yeah, this is a process. Let me copy this matrix again, 403, 302, 2, -1, 5, 9, 1, 11. And we want to multiply with a matrix that cancels this 3, that annihilates this 3. Now, we cannot use this 0 because 3 minus 0 is still 3. That does not get rid of the 3. We have to use this 4. So the first row remains as is. The second row remains as is. That's what that means. The third row, okay, we need to have a 3. So we need to multiply the first row by 3 to get the 3 out, or to get the 3 in place. But it has a 4, so we need to cancel the 4, to get rid of the 4. And we need to subtract. And we're going to do that to the third element, or to the third row. So we're going to take the first row, multiply by -3/4, because that causes this 4 to turn it into a 3. And not only that, it is going to turn into a -3. When we add with this row, we're going to end up with 0 in this position, which is exactly what we want. Now, there's going to be sequence, there's going to be consequence of that, but that's okay. So I'm going to call this matrix 1 because we want to keep track of our matrices. The first matrix that achieves the goal of getting 0 in this position is I'm going to label it as matrix 1 because we are going in that order. Matrix 2 will be this one. Okay, so let's go ahead and multiply this out. We're going to end up with 4, 3, 2, 9, 4, 3, 2, 9, 0, 0, -1, 1. And then here's where it gets tricky, because now we got a fraction. Unfortunately, oftentimes we cannot get away from the fractions. So -3/4 times 4 is -3, plus nothing with this, plus 3, that's going to give us 0. All right, -3/4 times 3 is -9/4, plus nothing, plus 2. -9/4 plus 8/4. That is -1/4. Okay, now this guy, -3/4, so that is going to be -3/2 when we multiply by 2 because the 4 simplifies with the 2. So -3/2 plus nothing even though there's a negative 1 here, the 0 neutralizes this guy. So negative 3 halves plus nothing plus 5. Negative 3 halves, negative 3 halves plus 5, that is negative 3 halves plus 10 halves, and that is 7 halves. Okay. Oh. And then negative 27 fourths, nothing, plus 11. Negative 27 fourths, negative 27 fourths, plus 11, negative 27 over 4, plus 44 over 4. 14 minus 7, 7. 3 minus 2, 1. Positive 17 over 4. Okay, so this is our second matrix, and it got us closer to having an upper triangular matrix, because this matrix was not upper triangular to start with. The original matrix, it has no zeros here whatsoever. After our first iteration, or after our first step, we got a 0 there, yeah, and a 0 there. Now we got, see, here we got 2 zeros. Now we got 3 zeros, but they're placed incorrectly. Notice that this guy, yeah, it would be up, this matrix, the square matrix corresponding to the main coefficients, to the regular coefficients. Remember, those are the constants. So this matrix is not upper triangular. We need a 0 there, but we already have a 0 there and another 0 there. So if we just swap those two, that will do it. Okay. So we're going to come up, I'm going to rewrite this. 4, 3, 2, 9, 0, 0, negative 1, 1, 0, negative 1/4, 7 halves, 17 fourteenths, 17 over 4 rather. And we want to multiply with a third matrix. So I'm just calling it M3. And our goal is to swap those two. But that is not a problem. So this row means pick the first entry on each one of the columns. Now I want to pick up the last entry. Well, no problem. Just do this guy. And that will pick up and place it on the second row. And then we want to pick the middle entry. Yes. And that will, we pick the middle entry. Yep. And that will place this middle entry in the third position, in the third row. Now, please don't keep putting equals. This is not equal to that. I did not claim that. Be very, very careful with your writing, please. When you put an equal, make sure that you actually have an equation. So the product of those two is equal to that. Now I'm going to change that, so I have to start a new equation. This times this matrix equals that. I want to change that, so we need a new equation. We cannot claim that this is equal to this, because that is not the case. If that was the case, then those two matrices would be equal, and they're not. You know, there's a 3 here and there's a 0. They're not equal. All it takes is one entry to be different, and then the whole thing is different. Okay, but this will take no time. You know, 4, 3, 2, 1. So 4, 3, 2. I meant 9. I think I said 9, 1. So let me double check. 4, 3, 2, 9. And then we're going to pick the last element in each column. So negative 1/4, positive 7 halves, positive 17 fourths. And then we're going to get 0, 0, -1, 1. Okay, but there's a lot more to this we have to discuss. Whoa. Okay, so first, the solution, it can be found by back substituting. So we know z, this is negative z. So we know z has to be, well, negative z is going to be 1. So that means that z is -1. Okay. So if z is -1, maybe I have to do a little bit of a computation. So I'm bringing back my site computations sheet, because there's a lot of little computations we have to include while we are doing this. So we have -4th of y, -1/4 of y, plus 7/2 of -1. So that means -7/2. And that is equal to 17/4. So if we add this to both sides of the equation, well, mind that this is 14/4, and 14 plus 17 is 31/4. So this translates into -1/4 y equals 31/4, which means y would have to be -31. We're going to check all of this in a moment anyway. So to be sure, y equals -31. And then we can figure out x from that. So 4x's plus, let's write that down here. I'm running out of space. I'm going to use the back of this page. Okay, so 4x's plus 3 times -31 plus 2 times -1 has to be equal to 9. Now, again, this is the column of the constants that go on the other side of the equation. So we understand that, and that's how I can tell that's the guy that goes on the other side. All right, so 4x minus 93 minus 2 equals 9. 4x minus 95 equals 9. 4x equals 9 plus 95 is 104. So that means x has to be 26. Now, before I claim to be victorious, we have to check that our original matrix equation works under these numbers. So we got that x equals 26, y equals -31. Just want to, oh, it's right here, -31, and z equals -1. So 4 of those is 104. Let's see, 104. 3 of those added together is going to be -93, and 2 of those is -2. So I want to make sure 95, sure enough, that's 9. So the first equation checks. Okay. 4 of those, again, is 104. 3 of those, again, is -93. And 1 of those, well, if we subtract 2 and get 9, and we subtract 1 fewer, that means we're going to get 10. So that checks. 3 26s, that's 78, because 3 times 25 is 75. So 78. 2 of those minus 62. 5 of those minus 5. 8 minus 7 is 1. 7 minus 6 is 1. So it checks. Okay. So before we continue, and there's more to do with this one problem, we wanted to make sure that the answer was accurate, and it is. All right. So what we want to do, though, is be able to multiply on the left, because we're not quite going to get the inverse yet. We're going to get something that is similar to the inverse, but not the inverse yet. Why not? The inverse matrix will give us the answers in one shot, in one multiplication, but we're getting closer to an inverse matrix. And that's what we want to get to. So we did 3 steps. Multiply with M1 on the left, multiply with M2 on the left, and then we multiplied with M3 on the left. Can we consolidate all of those matrices into one matrix? So we're still on example 3, and the question is, can we consolidate all 3 matrices into one matrix? And the answer is absolutely yes, we can do that. We got to be careful though. So M1, and we're going to do that now. M1 was 1, 0, 0, negative 1, 1, 0, 0, 0, 1. That was M1. And we multiply that on the left of the matrix of the system. All right, then M2 is going to be multiplied on the left, because after multiplying this on the left, then we again multiply it on the left. So it is a left on the left on the left. And that is very important, because matrices are not commutative. So the way we multiply them is extremely, extremely super duper important. So we have 1, 0, 0, 0, 1, 0, negative 3 over 4, 0, 1. That's M2, our second matrix. And then we multiplied with M3. And remember, M3, we're still under the same example, is this one where we simply swap the second and the third row. So we have 100, 001, 010. Now the question is, can we consolidate into one matrix? Yes, we may, we can. We have to multiply all of those together. Okay, so we're going to go ahead and multiply them together. Now, multiplication of matrices is associative. So we could do those two, or we could do those two first. It doesn't matter, but we cannot swap them. It is multiplication of matrices is associative. It is not commutative. So I'm going to keep this guy last. And then we're going to multiply here. So 1, that just picks the first row. So the first row will be 1, 0, 0. The second one, let's see, 1, negative 1. So that just picks the second row. Okay. So the second row is negative 1, 1, 0. Negative 1, 1, 0. And let me double check. So yep, yep, yep. The third one is the tricky one because of the fraction. So negative 3/4. Ignore this guy because there's a 0 here, and then add it to 0. So negative 3/4 times 1 is negative 3/4, which we added to 0 and 0. Oh, the nice thing is that negative 3/4 is not involved anymore. So we have 0 plus 0, 0 plus 0 plus 1. Okay. And then we swap those two. So we have 1, 0, 0, negative 3/4, 0, 1, negative 1, 1, 0. All right. So there we go. So this, can we consolidate? Yes. If we multiply the original problem, remember, this was our original problem. We multiply only once with this matrix, only once. We would save ourselves from doing this, and this, and this, and we will actually directly get to this point in one shot. Instead of doing 3 steps, we could do it in 1 step and achieve this, and then back substitute to obtain the solution. So is it possible to do that? Yes. Is it possible to consolidate in all the equation manipulations to get to an upper triangular setup? And the answer is absolutely yes, we can do that. So again, this is a lot of work initially, but it will pay off, because then we will be understanding matrices better. I believe one of the things we're going to get to do eventually is go the other way. Can we factor matrices back into simpler matrices? Those are simpler matrices than that one. That is a complicated matrix. So can we factor them back? And if so, how do we go about doing that? I think that is an interesting concept to think about. Practice this. Practice getting the matrices that do things to other matrices. And our goal is to obtain upper triangular systems, such as this one. Well, let me just write down what we ended up with here. So this is just to show you. What we end up with is the system of equation, the matrix equation, 4, 3, 2, 0, negative 1/4, 7/2, 0, 0, negative 1, x, y, z, 9, 17/4, 1. So if we start with where's my system? There's my system. My original matrix equation. Multiply this once on the left. We obtain this new matrix equation, and this matrix equation is more easily solvable by back substitution. Practice this. This is not, in my opinion, it is not trivial. This is not obvious. It is not easy. It is not intuitive, at least at first. After a little while, then we build an intuition for matrices. But initially, it is not. All right, we'll stop the video here.